Alright, so we're going to take a step back today and focus a little bit more on the calculus concepts. And we're going to start off with U-substitution, which is one of the, or maybe the first technique of integration that you're going to cover in your Calculus 1 course or the AP Calc AB course. And it's for good reason. It's essentially what I would think of as reverse chain rule. And the only way that U-substitution works is if there is a function in the integrand that is multiplied by its own derivative. That's the basic conditions of how it works. So, like for example, we have f of x times f prime of x dx. In this case, this function, we have the derivative, and we're going to do a substitution where we're going to say, okay, this is really u. We're going to let u equal f of x, and then we're going to take our derivative with respect to x. So du over f prime of x is equal to dx. So this is the first part of actually doing u sub. So you're going to take a substitution. You're going to let u equal f of x. And with these now, we're going to substitute these in. So this goes up to here, and this goes up to here, right? So our resulting integral is just the integral of u times f prime of x dx over, or du over f prime of x. And you notice that when we make this substitution, we can completely erase the f prime of x's, and it just becomes a simple integral that we can actually solve using the basic integration formulas and rules of integration. And so we can obviously get to this point, and this will just be, when substituting f back into u. So this is the idea of integration by u substitution. This is exactly what you're doing. So yeah, this is a quick little derivation. So what problems are you going to be faced with when you have these u sub problems? So the first problem that you're going to probably see, or one of the first, is going to be some sort of polynomial irrational function. So for example, let's say you have x squared over x cubed plus 1 squared dx. And what you're really going to be, working with here, and why is it saying that my HD trial has ended? But what you're really going to be working with here is just, you're going to let u equal some part of this entire thing. Now, what do we notice? Well, you can immediately notice that this part right here, this inside, is pretty complicated. It's under, it's under a power. We don't really know how to integrate this. Now, what do we notice about x cubed and x squared? Well, the derivative of x cubed contains x squared, right? The derivative of x cubed is 3x squared. We have this x squared term. So what we're going to do is, use that knowledge, and we're going to actually let u equal this entire thing. And whenever you can, always include the constant that's tagged into the polynomial, because when you differentiate the constant, it's going to become 0. And also, if you didn't leave out the 1 here, it would be the integral of the denominator would be u plus 1, and that's just a little bit more complicated than usual. So we're going to let u equal to x cubed plus 1, not squared, because that's gonna do some things to this derivative. And of course, our derivative with respect to x is 3x squared. And this left-hand side is pretty important. You're taking the derivative of u with respect to x, okay? And the reason I'm doing this is because when you rearrange and you're going to solve for dx, So dx is just du over 3x squared, okay? The reason I'm writing this all out is because, some people just go straight to like plugging things in. When you're good at this technique, you're gonna know what to do like very quickly. But we're gonna replace this with du, and we're gonna let this be u. And I want to show you the entire process of what's going on here. So we have our, we know what our dx is, and we know what our u is. So let's plug everything in. So this is just the integral of x squared over u squared du over 3x squared, right? This is what we just plugged in. This is the same thing right here, okay? And we notice that we can now cancel an x squared out, and this is just the integral of 1 over 3u squared du. And for those of you who liked, making things even easier to read, you can bring out this 1/3. It's just a constant in the integral and the integrand, and the integral of 1 over u squared du is all we have in the inside. From here, all we're going to do is just, do some basic integration rules. You can integrate this. Some of you might just do this and then do the integration, making it a negative exponent. I memorized this integral. It's just negative 1 over u. So our final, of course, with the plus c. And when you're doing an u sub in an f or q, or you're trying to show work, make sure that you're showing, even when you're not substituting the function with respect to x back in, include the plus c. Okay, it's good for work. And so then we're just going to have negative 1 over 3 times x cubed plus 1 plus c as our final answer. After we're just plugging in this back into here. Okay, right? Very straightforward. Let's do another example. So suppose you have the integral of tangent of x dx. So in this case, there's not, so immediately what someone might think of doing is, okay, well, we don't even, we're going to let u equal tangent x. There's nothing else we can see. Well, unfortunately, you don't have secant squared in here anywhere, because you're going to, once you let your u equal something, you're going to find that derivative, and you're going to hope that whatever the differentiated x version of u is, so whatever, after taking the derivative of u, whatever you let u to me, you're going to hope that it can cancel something out when you fill in everything. But in this case, we don't really have that. So what we have to do is we have to realize that, okay, tangent x can be rewritten in other forms of trig. And particularly, this is the same thing as the sine of x over cosine of x dx. And now some of you might see, okay, now I see where this is going. We have a sine and a cosine term, and both sine and cosine are each other's derivatives. Obviously, cosine's derivative has negative in it, but you get what I mean. The negative one, the constants that come out with the u sub, those aren't the ones that are important. The question is, are derivatives of each other? Is there something present here? Now, what are we going to let u equal? So if those of you who think that we're going to let u equal sine x, you're unfortunately incorrect, and we'll see why. So if we let u equal sine x, our du is just going to be cosine x, and then dx here. It's really in the denominator. I just skipped a step and moved to the right. So our dx is just du over cosine x. So if we finish this integral, we have u over cosine x du over cosine x, and unfortunately we did not cancel it out because this cosine x is in the denominator when we solve for dx. So we cannot let u equal sine x, unfortunately. And there we go. So we're going to let u equal cosine x then. Our du will just be negative sine x dx. And from here, we can just solve for dx, which is just du over sine x. So we're really going to have the integral of sine x over u, right? This is where this came from. And our dx is just du over sine x. And now we see that the signs will now cancel out very nicely. And our remaining integral is just the integral of 1 over u du. And this is really, oh, and then I forgot the negative, sorry. There's a negative from this part included. So it's really the integral of negative 1 over u. And this is really just negative ln of absolute u plus c. Plug everything back in. This is equal to the negative ln of cosine x plus c. Remember, the integral of 1 over u is ln of u, because the derivative of ln of u is 1 over u. So that's a pretty handy, this is where your derivatives and your understanding of derivatives is really important, guys. So know the formulas, know the rules, know the techniques of differentiation, because they will come and help you out a lot, especially with the trig on the signs. They're going to help you a lot. Now, this is a very classic U-sub problem, tangent x, and often the result might be written as the ln of secant x plus c. And the only reason is because if you remember from algebra 2 or pre-calculus that the constant here, because of the properties of logs, can be moved up there. This is really the same thing as ln of cosine x to the negative 1 plus c, okay? Right? We can apply that logarithmic rule, and of course this is really just ln of cosine x, 1 over cosine x plus c, and of course this is just secant x. Okay, don't confuse this with cosine inverse, by the way. Those are completely two different things. This is not arc cosine, so that's why this is just something, in my opinion, I do not think these terms should be used. I think this is terrible. This is just use arc cos, way better. It's just my opinion. Okay, so let's do a couple more U-sub problems here. So let's say we have the integral of xe to the x squared dx. Okay, so from this integral, you're gonna, now you, at this point, you're going to probably have a good guess of where this is going to go. So notice, so whenever you have U-sub problems, think about, what are the similarities between certain functions? What can I see? And you might notice, we have an x squared in the exponent and x. Those are pretty closely related. Okay, so in this case, we're just going to keep going. We're going to let u equal x squared. And for the record, guys, before we continue, at first you might not know what to make u, but if you keep trying U-sub, like you can start by trying to make u that, and you can do whatever you want. All I'll say is you can try a lot of things. It'll waste a lot of time, but you can get the right answer even if you get the u wrong. Like for example, in this case, you might have let u equal sine x, and you might have gone, you might have been like, wait, that's not really going anywhere. If it doesn't go anywhere, don't be like, oh, am I doing something wrong? Most of the time, it's going to be the case that you're just not letting the right thing be u. Or it's not a U-sub problem, but that's a different story. If you're in Calc 1, no need to worry about that. Okay, so for here, we have u equals x squared, so our differential with respect to x will just be 2x. And solving for dx, we're going to get du over 2x, okay? And of course, just plug all those in. We now have the integral of x times e to the u du over 2x. Once again, the x's are going to cancel very nicely, and we now have the integral of e to the u over 2 du, and this is just 1/2 e to the u plus c, and of course plugging what we made the substitution for u back into the final result, we will have the 1/2 e to the x squared plus c. Now I just want to clarify, like, this is, if this integral just didn't have this x, it would be a completely different story. It's actually insane because it would actually, this integral in and of itself is quite the impossible integral. In fact, the result is an error function, but that's just something that I want you guys to search up on your own for your own research purposes. Let's do another case here that you might come up across. So let's say you have an integral of 4w plus 3, or let's do x, but 4x plus 3 over 4x squared plus 6x minus 1 with respect to x, of course. Now in this case, you're going to be like, okay, oh my god, what is this? Do I have to let u equal 4x squared? What do I have to let u equal? You can let u equal an entire denominator, guys. And in fact, what we're going to let u equal here is the entire denominator. So in this problem, notice that if we differentiate this, we're going to be left with a linear term and a constant, because this 1 will go away, this 6x will turn into a 6, and this will be turned into 8x. Okay, so let's try it. We're going to let u equal 4x squared plus 6x minus 1. In these big polynomial rational functions, guys, generally u will be the big denominator, because you'll notice there's going to be, after you take a derivative, that there's going to be some factor of the numerator or something that you can cancel out. So du is just 8x plus 6 dx. But wait, that doesn't really look like 4x plus 3, or does it? Because du, let's factor out 2, and what we're going to notice is that we're just going to have 4x plus 3 dx, and that's exactly what we're looking for. This is what we're going to be able to cancel out. Okay, so if we solve for dx, we're going to get du over 2 times 4x plus 3, all of that in parentheses. Okay, so now when we substitute everything back in, so let's quickly do that. We're going to have, this is the integral of 4x plus 3 over u du over 2 times 4x plus 3. So now we can cancel these guys out, and all we're left with is a half from the differential term, and this is really equal to 1/2 the integral of 1 over u du, bringing this half out in front of the integral symbol. And this is just 1/2 ln of absolute u plus c, and furthermore, plugging our x values, or our x's back into u's, it'll just be 1/2 ln of 4x squared plus 6x minus 1 plus c. Okay, so there you have it. So that's one of the other types of common integrals that you're going to see. We're going to do one more here, and we're going to do something that's, let's do something a little bit more complicated. So this is the different type of, once again, there's going to be a lot of examples that, and I think I will link a practice sheet for these integrals, but in the future, might not be, but at the time of this uploaded video, but I might post some other stuff. but this integral will make you think a little bit outside the box. And it's going to be the integral of x root x plus 7 dx. So, okay. Now, the way to let's say you couldn't do U-sub. The actual way to do this is to foil out the foil this out and just say it's or actually I don't think that's even that actually doesn't work. Okay, so anyways, what we're gonna do here is we're gonna do a U substitution. Now, if we let U, so generally in the previous cases, we've always let U equal like the most complicated thing in the function. Like what's in the exponent here, the x squared in the exponent, the, in this problem, there's something in the denominator squared. There's a lot of terms there. And that's what we kind of let everything equal to. But in this case, we can't really let U equal x plus 7. Now just a quick reminder that the derivative of root x is 1 over 2 root x. So in this case, if I let U equal root x plus 7, we're just going to get du as 1 over 2 root x plus 7, and we don't have to worry about a chain here. The plus 7 is, and the derivative of the inside function is 1. And this doesn't really help us out, because if we, and actually it does, and there's there's actually two main ways to approach this. So if we do let U equal this, right, so we're going to plug everything back in. So we have x times U times du over 2 root x plus 7. What we're actually going to have to do here is actually plug in U back into this denominator. So this is really the integral of x times U du over 2u. And just cancel these out, and we're going to have the integral of 1/2 x. Me personally, it doesn't, there's something odd about that method that I don't feel very comfortable using. So the way I would think about it is, okay, we're going to let U equal x plus 7. We're going to let du just be dx, right? It's just 1. The derivative of x plus 7 is 1. Now, what is x in terms of U? Well, from here, we can just say that x is U minus 7. Okay, now let's plug everything back into the U world. And so this is really the integral of U minus 7, right? This is our x and x term, times our U, right? So that's this term, inside term. And of course, our U is to the 1/2 power. And then our du is just dx, so there's nothing to really worry about. So now this is our new integral when we let U equal x plus 7. And now look at what we can do. We can now distribute this U here, because this is to the 1st power. So there's no foiling needed for the U minus 7. Up here, I can't distribute x to the, to the root x plus 7. I can't distribute to this, right? That's not how math works. But in this case, I can, because now I'm multiplying a singular term by a linear term to the first 3. So this is really now the integral of U to the 3/2, right? From this to this. It's U to the 1/2 times U to the 1, which is just adding the exponents, minus 7 U to the 1/2. And now this becomes a simple polynomial integral, which we can just do by the reverse power rule. So it's going to be 2/5 u to the 5/2 minus 14 over, I believe, 3 times u to the 3/2. Yeah, that should be right. And then we're just gonna tag on the plus d, and it should be 2/5. Now we're gonna plug in our u again, so x plus 7 to the 5 over 2 minus 14 over 3, x plus 7 to the 3 over 2 plus c, and there's our final resulting integral. And so you see that there are cases where you can't just plainly let u essentially just equal what just whatever you want and hope that it's going to cancel something out. Sometimes you have to do some manipulations with your substitutions, and I didn't write the 7 there. So I want to leave you guys with this integral, where we have the integral of root tan x. And all I want you to guys know, in terms of the hints to how you're going to approach this problem, let me just move this to the right, is that you're going to make a u substitution of the entire function, in fact. And what you're going to do is you're going to square it. You're going to square it. You're going to make it to the 4th power. And then you're going to turn this part into secant squared x minus 1. And from here, I'm going to leave you to try this problem. It is a super long answer, but it will test your calculus abilities. And this is really testing your ability to go past just making a general u substitution. So give it a try. Anyways, guys, that's all for today. I'll see you guys in the next video.